Hello, it's a short video to share a presentation I gave to the International Energy Agency Annex 94 meeting in spring 2025 to present the results of quite a large performance gap study between the predicted and measured whole building heat loss of several hundred dwellings. So all of the comparisons are done using BTS's Smart HTC products. This is a way to measure the heat transfer coefficient, the total rate of heat transfer between inside and outside a building using monitored energy and internal temperature data. And the important thing is that the building can be occupied as normal. That data can come from smart meters, from smart thermostats, so that the data collection is almost accidental in a lot of cases, and it really collapses the cost of doing the measurements. It's been available since 2021. We've measured just over 11,000 buildings. We've got more than 100 users, and you can see a breakdown of how they're made up. So some researchers, but a lot of consultants, surveyors, people wanting to know more about how buildings really work. It's a cloud-hosted calculator, and it has two ways to access it. It has a simple-to-use browser user interface, so that anyone off the street, even a thicko like me, can operate it. And it also is available for API integration, so you can, if you want to integrate it into a service you already have, you're collecting that data already. You can do near instant HTC measurements with data you're already collecting. Bit of background on Smart HTC, just to show that the results I'm going to present are relevant and accurate representation of how buildings perform. As I said, it's an in-use energy balance, so it uses data collected while a building's in use, or it can be empty or it can be occupied. And it's an energy balance, so it infers the amount of heat transfer from the building by measuring the amount of heat input to the building. And here's a chart showing 43 comparisons in different dwellings of lots of different levels of thermal performance, so ranging from passive house flats up to quite poorly performing buildings. And these are comparisons with the coheat test, so the best in class, most accurate way of measuring HTC. And we've got a really close agreement here. So here, the accuracy 0% would mean that there was 0% error. It's perfect. So we've got an accuracy of 1%, which shows that there's very little bias between over or under estimating the amount of heat loss, and a precision of 12%. So that's the average dispersion from the right answer, and 12% is a pretty high result using this metric. So it's quite a precise and a very accurate measure of how much heat loss there is from a building in winter or heat gain during summer. And the performance gap sample I'm going to present the results of is around 500 buildings, and the comparator is the measured heat loss using Smart HTC and the predicted heat loss using RDSAP, reduced data standard assessment procedures. So it's the UK's standard way of producing EPCs. I guess most people interested in this video would know how that works, but basically it's a visual survey of a building, and then you, based on the appearance of the construction type and a measurement of the size of the building, you estimate the thermal performance of the building. So you measure, I've got this many meters squared of this type of wall, look up in a lookup table what the average performance of that wall type is, add all those heat losses together, and that's going to give us a predicted heat transfer coefficient that happens every time an EPC is produced. There's a really great open access database of EPC data, but very sadly, the HTC is not stored in that database, so it's not that easy to directly compare from an EPC what the predicted heat loss of the building was. That's just a really simple thing that we should fix. And here's a sample. It's a really mixed sample, lots of different ages, but focused in the sort of post-war periods, so 50s, 60s. Lots of different building types, construction types. So quite a mixed sample, by no means representative of the UK housing stock, but a reasonably mixed samples, lots of different types of buildings, and there are lots of different types of building performance, levels of building performance. It makes a total sample size of 503. And the RD SAP HTC calculations here were done by the Energy Savings Trust in a project that we did together. The sample's got a slight bias towards older buildings, but here's the results. So across these 503 buildings, there's an okay agreement. So you can see in that X versus Y plot, there is some sort of trend there. So the RD SAP method is categorizing which are the best buildings and which are the worst buildings at a reasonable rate. But some of the X's there are well away from that solid black line, which is X equals Y, where the prediction would match the measurement. And actually 57% of all of those 503 buildings, the performance, the measured performance was different to the prediction for those 57%. So for only 43% of the buildings, the predicted heat loss was right. So more than half the time the prediction is wrong, but on average it's not too bad. When it was wrong for these buildings, for 72% of those buildings where the measured heat loss didn't match the prediction, the heat loss was less than expected. So the building performance was better than predicted. So there's a lot of buildings out there where the building is actually better, has less heat loss than we expect. On average, the gap between the prediction and the measurement was 30%. So on average, we're 30% out. For some of the buildings, it's an enormous gap. And for some of the buildings, it's right. Here's a little bit more of an insight into that. So there was a gap between the prediction and the measurement of the amount of heat loss, so the performance gap of less than 25% for half of the houses. So for 47% of the houses, the performance gap was more than 25%. And there were some where the gap was enormous. So 2% of the houses, the gap was more than 100%. The prediction was 100% wrong. For another 2%, it was between 75% and 100% wrong. And there was 12 plus 2 plus 2. So 16% of buildings where the prediction was more than 50% wrong. So it's easily possible to get complete incorrect assessments of how much heat loss there is from a calculation like this. And you can see that gap doesn't seem to have any real significant relationship with the SAP rating bands. So buildings with better thermal performance, in this case, actually performed better than predicted, probably because we're using the more blunt instrument RD SAP rather than a full SAP assessment with the knowledge of all the predicted U values of the new builds that are likely to be in that A rating band. But there's a gap for every rating band. It doesn't work perfectly for some and not for others. This isn't the first performance gap study, but it is the largest so far. So combining two previous studies, one from Leeds Beckett University and one from the State of the Nations project, we can get a sample from a previous project, those two previous projects of 84, and these had a significant bias towards new build dwellings. And you can see there that there is also a relationship, so that RDSAP is categorizing those buildings okay, but it looks again that there's quite a few that are away from that solid X equals Y line. So in this case, 70% of the buildings were outside of the measurement interval of the prediction. So you can say that the predicted heat loss was wrong. And of those, 85% were worse than predicted. So for these new builds, it tends to be much more common to have more heat loss than predicted. And the average performance gap there was 31%. So although it was more common for them to have more heat loss than expected, the average performance gap was actually really similar to that larger sample I just showed. And also the amount outside of that confidence interval of being the right answer is quite similar-ish as well. So some similar trends emerging between the two studies. If we go ahead and combine those two together, we can make an assessment of how well RDSAP is working. So the accuracy of RDSAP, remembering here that low numbers are good, it means 0% error, is 8%. That's actually pretty good. So RDSAP, which is a reasonably basic energy model, is doing quite a good job on average at categorizing which are the best buildings and which are the worst. So that is positive, and that is really what it aims to do. That is the aim of producing it. But, big but, the precision is 38%, and that's really quite a big number. And what that's saying is that we're pretty good on average using RDSAP, but we're really pretty poor if you're thinking about individual buildings. So although on average we might be right and we don't have a particular bias either way, or a strong bias either way, for individual buildings, it's really common for the heat loss to be completely incorrectly assessed using that survey. So I think in conclusion, you could say that RDSAP is really useful for looking at groups of dwellings, which after all is what it was designed for, but it's pretty poor as a tool for looking at individual dwellings. And the sort of knock-on effects that can have is it really risks misdirecting retrofit spending. So if we can't identify which buildings most need help, we could be spending money on buildings that are actually much better than we think they are and don't need as much help. So in that study I mentioned with the Energy Savings Trusts, they estimated that the performance gap would mean that £60 billion worth of retrofit funding to get buildings up to a SAP rating of C would be misspent on buildings that are already there. So you can get really big amounts of money that we could put in the wrong place. And of course, that has all the knock-on effects. Like if you have someone in a building that is worse than expected, they won't be the target of retrofit funding because the RDSAP assessment has incorrectly decided that the building has quite low heat loss. They will therefore be at risk of things like fuel poverty and will be missed out by the policy tools which are designed to find them and help them. Similarly, if you're looking at pre and post retrofit, we're really going to struggle with quality assurance if we don't have a tool that can look and accurately measure the performance of a single building. And that means that long term, we could repeat errors. We could be doing retrofit measures which don't actually improve the performance of buildings as much as we think and never know it because we don't have the accurate tool that a measurement would be to tell us whether it worked or not. And then as we move to heat pumps and sizing of the heating system becomes more important than it was when we were using gas boilers, you can see that a calculation tool like this, and we've used RDSAP here, but if you used 12831, the relationships would be exactly the same. We're going to have an issue with accurately sizing the heat loss for a particular building. So this sort of performance gap study starts to hint at some of the reasons why performance measurement can be so valuable to improve things like deciding what to do with a particular building, your retrofit planning, checking whether your retrofit worked as planned, new build quality assurance, does the building perform as I expected it to? All those things that aren't so good using an energy model because you need something precise about the building itself. Thank you very much for listening.